Good morning, good afternoon, good evening, good day, everybody, wherever you might be. Today is my pleasure to introduce Paulo CARRILLO ROUSE from France, from Orleans. Oh, hello, Paul, you're also here. Yeah. And he will tell us about an MCG approach to index theory for manifolds with corners. So please don't put us into a corner. Please explain everything.
Yeah.
The floor is yours. Take it away.
Thank you very much, Peter, for the nice introduction, and thank you very much for the opportunity to speak in this international seminar. So I will do my best to explain details, but of course you are free to ask me every question you want. Maybe I won't answer, but I don't know if I could answer, but I will try. I'll do my best. So I will speak about some work I've been doing with mainly with Jean-Marie Lescure from here in France, but also with Mario Velasquez from Colombia, and well, our approach to index theory for manifolds with corners. So it's about really the use of non-commutative geometry and especially groupoids. So just let me start by telling you what is a manifold with corners for me, or at least in this talk. So let me see if I was staying here. Yeah, so it works. Yeah. So for me, a manifold with corners will be a manifold with embedded corners, which is already a very interesting case of manifold with corners, which is then a Hausdorff topological space, which is in fact given by the following data. So there's a smooth manifold in which the space is embedded, and so it will make sense to speak of C-infinity functions up to the boundary. And to have an image, in fact, well, I consider the case in which the hyperfaces are defined by what is called a family of functions, so like that, of defining functions of the phases, which essentially will measure the distance to phase. So you have an image of this is like sorry, let me take my tablet. So it could be like the intersection of several hyperfaces, and so what is in the interior, well, in the intersection is what can be called a manifold with corners. So it's what is said here, right? And with some nice condition on the intersections, because we don't want to have too much trouble in these intersections. So, for example, we ask that this condition, so the differentials of the defining functions that define the hyperphases are linearly independent for every point. So that's to avoid problems in the intersections. So this is an example of, well, this is the manifold with corners, which I will consider in the sequel. And well, I will tell you some motivation of the index theory. So part of the motivation will be about geometric analysis. I will mention some ugly words about sort of differential calculus and all that, but eventually we'll come more to the non-commutative geometry approach. But for starters, let me, oh, sorry, so this does not erase, right? So I have to erase it every time. That's weird. Okay. So so let X be a manifold with corners. Can you see the actual screen? Because I don't see the.
Yeah, okay. We see the screen. Yes. Okay.
So I take a manifold with corners. So let me just motivate the problem that I will try to tell you about, the problems in index theory. So in this context of manifold with corners, so as the objects I was introducing in the last slide, so there is a calculus. So there are algebras around. So algebras in particular developed by many people, Melrose, Piazza, Schulze, many other people that have defined through the years the appropriate algebras of pseudo-differential operators, for example. So that means that there are algebras around of operators, symbolic calculus. There's all this study about ellipticity and full ellipticity that I will mention a little bit, but not too much, and Fredholm problems, which is related to my talk now. And for example, in the case I am interested in this talk, it's about especially what is called the B calculus, because there are several different calculus for different manifolds with corners. But in my talk, at least, I will speak about the B, so the differential operators, which will not appear explicitly, because again, this is just for motivating my talk, but I will really talk about non-commutative spaces. But the idea behind of the motivation comes from these pseudo-differential algebras. And in particular, the pseudo-differential operators, just to give you an idea of what they are, they refer to the operators which are obtained by micro-localization of the Lie algebra of infinity vector fields, which are tangent to the boundary. So that means that essentially you consider for having an image, you can see the differential operators, which are V differential operators are the ones that are generated by the vector fields in the manifold with corners, which are tangent to all the faces. So what else? Well, in particular, there are algebras and C-star algebras, which brings us a little bit close to non-commutative geometry. So there are algebras, there are exact sequences. In particular, there is a short exact sequence associated to the pseudo-differential calculus. So that this is notation is quite classic in geometric analysis. The closure of the zero order pseudo-differential operators are bounded, so you can close it in the bounded operator topology, and you obtain an exact sequence like this. I will describe this kernel after. And so there's this symbol map. This is commutative algebra in the right-hand side. And these sequences measure what is, the ellipticity. So meaning that an operator in this calculus in the middle is elliptic if its principal symbol is invertible. So meaning that essentially it's invertible up to this subalgebra, which is not compact operators, but is what I will call in the talk B-compact. These are not compact operators in the case of even manifold with boundary, which is a case of manifold with corners. So I will, in fact, present this algebra later on as an algebra of the C-star algebra of some groupoid, which this is well known from a long time now, more than 25 years maybe, that this kind of calculus can be presented differently by using Lie groupoids. But just to mention about the B operators, well, these are not compact operators, but this algebra contains contains the compact operators in these cases, for other groupoids as well. But in this case that I am interested today, there is a sequence like that. So meaning that there's the compact operators here on the left, and the other algebra is the quotient, but it will appear later on as also as a C-star algebra of some particular Lie groupoid. But the point for me to mention this sequence is that if you are interested in the problem of ellipticity, so meaning that you want to understand the operators which are invertible up to this algebra in the middle, then since the compact operators is a subalgebra, among these elliptic operators, there are those which are for which the quasi-inverse is already in the compact operators. And in fact, these are the ones that are in fact Fredholm operators in the calculus. This is in geometric analysis. This also is called full ellipticity. I mean, well, some people show that in fact full ellipticity in principle is a slightly different notion about some non-commutative, about the invertibility of some non-commutative symbols, and but essentially is Fredholm. You have to prove that. It's very classic in geometric analysis, for example, in the case of. So again, all this is just motivation for. I haven't really started the talk, just motivation problems. So full ellipticity is about some condition of invertibility of some symbol that I will mention later on again with non-commutative spaces. But essentially it's Fredholmless. So in every calculus that we know, not only for manifold with corners, but other kind of calculus for singular problems, full ellipticity is usually related with Fredholmless. In this case, is the case. It was proved by PAULO in 2005, perhaps already by Melrose Piazza in some previous paper. The point is that, well, among these operators, there are those which are Fredholm. And not every operator in the calculus is Fredholm, even not every elliptic operator is Fredholm. But one of the problems that I will try to address in terms of K-theory and some index problems is the following, but I will need some terminology. So given an elliptic operator in the calculus, well, we say, sorry, there's a question?
Yeah, just a trivial question, sorry to interrupt, but what's the difference between elliptic and fully elliptic?
In fact, for my talk, fully elliptic is Fredholm. So meaning that
okay.
You know, the ellipticity is the invertibility of an operator up to this algebra.
Yes.
But this algebra is not the compact operators. It contains the compact operators.
Okay, I've got you. Yes, yes.
So that means that among the elliptic operators are those who are invertible up to compact operators, and these are called fully elliptic.
And would it be a good model to think about that you can take a torus and divide it by an appropriate Z2 action, and then have something like a pillow, so it's topologically a sphere, but as it's not really a manifold, it has these four corners. Would it be a good model to think about this?
Maybe I don't know, but I don't know if I'm following your idea. But maybe, I mean, one thing that will appear, I mean, the idea is to be invertible at the infinity, so at the singularity. So that's I don't know if this is something that, you know, because here in this case of manifold with corners, or the case you were mentioning, there's a topological boundary, which is somehow the singularity. And essentially this condition is to, I mean, being invertible here is that, sorry, being invertible up to this algebra it means that essentially it's invertible at the infinity, so at the singularity. But well, this is just to having an idea in mind, but it's not to be precise. The definition of full ellipticity can be just well, I would not mention it because it requires the definition of a non-commutative symbol. But, well, ellipticity plus the invertibility of non-commutative symbol, but you can show that full ellipticity is equivalent to be invertible up to well, it's elliptic plus invertible up to compact operators in the algebra.
I'm asking because it's a very simple and nice construction. You just, think of a torus as a square with identified edges, and you have some natural Z2 actions. Okay. And it enjoys, it's funny because it enjoys a nice theta deformation. I think Richard knows more about it. And then when you theta deform it, all of a sudden something what is topologically a sphere. So you do like a quantum sphere, but then K0 is Z6 because each corner contributes a generator after the deformation.
Okay.
So that's why it immediately came to my mind when you say manifold with corners. I think about the pillow and.
Yeah, it is a manifold. Pillar is a manifold with corners.
Yeah. Okay.
It's a special case.
Good. Yes. Good. Thank you.
Okay, I wasn't hearing the question exactly. Okay, then is that the case? Yes, the pillow is an example. Yes. Well, in any case, maybe we can discuss this example later. Of course, that's because then, well, let me get to the motivation of the problem that is related to K-theory afterwards. I will mention it. So I mean, in this calculus, so there's ellipticity and full ellipticity. So again, I mentioned this result of Loya to tell you that you can, in fact, think of ellipticity, fully ellipticity, sorry, in this talk as Fredholm.
I have a question.
Yeah.
Let's say there are no corners. We just have a classical closed C infinity manifold. This theorem of Loya, it is a fact that you can have a differential operator. There's nothing exotic. It's a differential operator.
Yeah.
This exists in great abundance on contact manifolds. These are differential operators, which are Fredholm, but they are not elliptic. I don't understand how that fits into this theorem of that you have theorem of Loya.
Okay.
These operators exist in great abundance on what are called contact manifolds. It
Yeah,
was
what you
by
mean.
me and Eric, my wonderful coworker, Eric Van Erp.
But I think that they're still elliptic in some sense, right? So it's a
Well, they're not elliptic. These are not elliptic operators.
no. In fact, here because the ellipticity here is just it requires this definition of the non-commutative symbol that I will not mention. But I think in the case you are mentioning, there's also a non-commutative symbol, right?
Yes, there is a non-commutative symbol. That's correct.
And in that case, I think this makes sense. So it's elliptic in that sense, if and only if it's Fredholm.
Okay, that's an interesting answer.
Yeah.
Okay. I mean, you're saying that if the non-commutative symbol is invertible.
Yes. Yeah.
Okay. Thank you
Yeah.
for that remark.
No, you're welcome. Thanks for the comment. So so again, well, the point is very interesting this because you might have operators which are elliptic but not Fredholm. And in some calculus, here I am interested in this problem of B pseudo differential operators, but some of these problems, I mean, as you will see, they're quite similar in other calculus, and certainly the K-theory methods can be applied in other examples. So the point is that if you, well, I will tell you a definition that will allow me to motivate the problem that I will try to address today, is that if you have an elliptic operator in the calculus, we'll say this, I am following the terminology of Victor Nister, his collaborators in some papers. Well, we can say that, we'll say that D satisfies the Fredholm perturbation property, which I will call FP, if you can perturb the operator by some regularizing operator in the calculus. So again, these are not compact. This is not, this B means that it's just regularizing in the calculus. So given by some smooth kernels, but with an appropriate sense of that. And such that the result is Fredholm. Such that you can perturb your operator to become a Fredholm. And well, just slightly more related definition would be stably Fredholm perturbation if the property is satisfied up to some adding some unit operator. So this is what will bring this to K-theory. So well, this is an interesting problem in analysis, in geometric analysis, to understand how to at least perturb your operator to make it Fredholm. So the question, sorry, I don't know why this is still there. I have to erase in every slide. Okay. So I will tell you what is first obstruction to Fredholmness. It's not of myself. This is again, a lot of people have worked on this. So the point is to understand the obstruction to this Fredholm perturbation property. So again, to associate it to this exact sequence of the pseudo differential calculus, there is an indexmorphism that, in fact, later on I will tell you, because this is just again motivation, but for me the indexmorphisms in K-theory are not directly given by the connecting map, because the connecting map is of course the index, but in the I would say the modern one of the modern ways of looking at the indexmorphisms is by using groupoids, and in particular the way I will tell you later on how to define these morphisms is through the what is called the tangent groupoid of Kohn. So there's some algebra in the middle that will realize this index somehow. So this is just to explain that in fact I'm here putting K0 and not K1, because usually the connecting maps goes from the K1 of this algebra to the K0 of the other. But in fact, this connecting maps factors by some morphisms given by some groupoids that I will later on explain a little bit more, or you can ask the questions. The point is that there is an indexmorphism, and what does it measure? Well, in fact, what this index measures, because, well, other thing to tell you about as other calculus is that this K-theory group, this is K-theory, this is topological K-theory of the B cotangent bundle. So maybe I didn't mention what is the B cotangent, but the B tangent bundle is a vector bundle over X such that its sections are exactly the vector fields which are tangent to the faces. So this is how, for example, Melrose consider it. And here I'm taking the cotangent. So it's known, it's quite classic in this domain that, in fact, this group is what contains, what codifies the principal symbol classes of B pseudo-differential operators. Just as in the case of Atiyah-Singer, the K-theory of the tangent bundle codifies the elliptic operators. So this is why this group is important to consider in this setting. So it's okay, so let me tell you some results that I will announce it in my way, but essentially it's due to Nesesinski, Savin, and Sternin, at least the first version of this result that I know, is that, well, if you take an elliptic B pseudo-differential operator on a compact manifold with corners, then this operator satisfies this property of being invertible, being elliptic up to, Fredholm, excuse me, Fredholm up to perturbation and perhaps up to stability. So it means that you add a unit identity operator, if and only if this index vanishes. So this is very common in index theory, right? So this indices measures some kind of default of invertibility. So in this case, this is the property. It's so this satisfies this property of being Fredholm up to perturbation, a stable perturbation, if and only if this index vanishes. So this is one of the main motivations for that we started with Jean-Marie some years ago to understand how to compute actually these K-theory groups and then the indices. Just to mention, well, in particular, if the operator can be perturbed to be Fredholm, then it's this index which I call the bounded analytic, because one can show, again, this is motivation. I will, if you ask questions, I will tell you more details, that the map restriction to the boundary, in fact, in K0, it's an isomorphism. This is some things that arrive, that happens in this case of manifolds with boundary or with corners. Well, of course, the case of manifold with boundary, I will mention it before, the case of manifold with boundary, in this is just zero, this group. What is interesting is from codimension 2, so when you have like squares or more. But I will mention this. So this is my motivation to, oh, sorry, this is a big diagram. I was not sure to present you, but I like it because, again, this is, I attribute this result to these guys, Nesesinski, Savin, and Sternin. There are different proofs of this. I know one by Nister. And in our group, in our paper with Jean-Marie, we did a groupoid proof, which is really, all these elements, this is just motivation to tell you that essentially it's just about chasing, diagram chasing. If you put this in appropriate terms and use appropriate non-commutative spaces, not only groupoid, but really non-commutative tangent bundles that I will introduce later, then you can prove this kind of theorems mainly by chasing diagrams and using K-theoretical properties, which are classic, like the existence of the 6-term exact sequence and so on. But I will not prove this term today. So just to tell you that that's my motivation to compute first these groups. So what are these groups? So the K-theory in general, not only the K0, but the K-theory of these algebras. And I will give you an answer today that I will been talking in some years, but I will give you also not only the K-theoretical computation, but at least in some examples, the index itself. But the index, it takes values in these groups. And since I was mentioning this is the abstraction to this problem, is then interesting to not only to compute the groups themselves, but the indices, given an operator to be able to compute the index. Okay, so just to mention some historical results on this. One of the first results I know, at least, is a paper of Melrose and Easter. And I mentioned they compute the first differential of what? Well, in manifold with corners, maybe you can imagine that there are natural filtrations, because you can filter the algebra by the codimension. For example, you can take a square and you can restrict the algebra to the interior, then to the interior on the faces, on the how do you call that in the sides of the square without the corners, and then the entire algebra. So there are natural filtrations that come with this. So in fact, Melrose and Easter, they have a very nice paper in which the main result is essentially the computation of the first differential, which is was not trivial at all at the time. Then, well, there's also a computation in terms of K homology of Nasesinski, Savin, and Sterling. So they give a way of transform this problem in K homological problems. It's quite not a standard, but in many other problems, this is done by many other people as well. But as far as I know, in their papers, they don't mention explicit computations. And then, well, there's also Montauban and Easter, which again, they use ideas coming from Bohm and Kohn, because these algebras, in fact, these are groupoid algebras, as I was mentioning, and they are very nice miniable groupoids, and essentially you can apply some Bohm-Kohn ideas to transform the computation in some topological K-theory computation, which is also possible, in fact, related to the solution that we gave with Lescure and Velasquez. But I will spend some time on it. I will tell you an explicit computation of these things that is based on the use of groupoids. But hopefully you will see that even without using groupoids, at least I can state the answer very simply in terms of just the manifold with corners. So I will try to do it. So just before passing to that, just let me tell you what I'm trying to tell you first is the computation of the K-theory groups. And well, of course, you know that in codimension 0 case, it's the K0 of the, I will put just the K0 just to mention things, to mention some example. I guess most of the people in the audience know that the K-theory of the algebra of compact operators. So this computation is quite classic, perhaps available even in the books of many books on K-theory. So it's the integers. And well, the index in that case is just it's just T Zinger, which is at the core of a lot of things. And so, well, in codimension 1, for example, in codimension 1, so meaning manifolds with boundary, this K0 group is 0. And this is known from a paper of Montauban and Easter, at least. It's 0, just it's an easy computation, but I would say that it's a computation which is easy, but it has deep consequences, because then in that case, you can always perturb the operators. In that case, there are no obstructions. And well, in that case, of course, the group is 0, the index is 0. So from codimension 2, as I will try to sketch in our computation, in fact, every possible value can arise in our computation. In fact, I will introduce a homology group, some homology groups, which we call the conormal homology of the manifold with corners, which will give the answer. And in particular, well, in codimension 2 will give just it will just given by some kernel of some differential that is well, it's included in this free model generated by the phases of codimension 2. So this is just for C below, but in fact, I will tell you the definition exactly of what I mean by H2 CN. So it will be the conormal homology of a manifold with corners, and I will tell you how we get to the computation. So again, this is something. The dimension 2 and 3 is something I did with Jean-Marie in a paper maybe 4 or 5 years ago, and using essentially the idea of Melrose-Nister, but using groupoids. So try to compute the differentials. So you have filtrations, and then you try to compute well, spectral sequences and all that. And it was really a nightmare, as usually it is with the spectral sequences. But well, we managed to do it up to codimension 3 and do some products, because at the end we guess the result and we come to these groups. That, as I will mention, it usually happens in mathematics. These groups are not new. Were not new because it appeared at least in a paper by Bunke that I didn't know at the time. But Bunke found these groups in relation with also with problems of manifold with corners and Dirac operators. So, and in codimension D, we solved it with Mario Velasquez completely, but rationally. And as far as I know, we cannot do better of codimension. We cannot remove these rationals in general from codimension 4, because there's a recent paper by Thomas Chick and Mario Velasquez in which they actually showed that there might be torsion. At least our methods don't apply. So, but I will I will tell you what this manifold, what this conormal homology is. I will try to convince you that this is a completely explicit object, almost combinatorial, and then to try to explain you how the K-theory of these B-compact operators can be computed using these homology groups.
Ray, may I have a question?
Yeah, sure.
So if this codimension is equal to 3, it is possible that we get something which is torsion or not?
It seems so. In fact, in all the examples that Jean-Marie and I was at least in the examples we knew, there was no torsion. But it seems that we couldn't prove it was not the case. And it seems that if you look, there's a paper which is in the archive by Thomas Chick and Mario Velasquez, in which actually I think they have examples with torsion. So,
so the torsion could start if the codimension is at least 3. Yeah.
Yes,
Okay.
But the computation of the K-theory, we can do it integrally up to codimension 3, even if there might be torsion. Yeah.
Okay, thank you.
And what's the difference between CN and PCN? What does it stand for with HCN and HPCN?
Sorry, I will define it later. In fact, the P is periodic.
Okay.
It's a periodization because yeah, I will define it later on, but it's here it will be simple because I mean the computation of the K-theory.
And CN, what does it stand for? Why is it CN?
I will define it in the next slide.
Okay.
So if I
will you give some concrete examples? Because I would like to see something more explicit than X. Yeah, I will try to do it. For example, I will give the definition and then maybe we try to compute some, at least in some examples. Okay.
Yeah, I think that CN stands for conormal, yes?
Yes. That's,
oh, yes. Yes. Thank you. Yes.
Oh, yeah. Sorry. That was the question. I was going to define it. Yeah. It's just notation that we put as conormal. This is, as I will mention, is not completely new, and some can be realized otherwise. But let me take a manifold with corners, and then I will try to mention an example. So we'll define you a complex, chain complex. So the complex will be giving as follows. So the P module will be generated by the faces of codimension P. So for example, if you take a square, so you have a F2, which is just the 4 points. This is F2, right? Then you have a F1, which is just the lines. And you have F0, which is the interior, right? And, well, for every, so we consider essentially the free model generated by the faces of codimension P. Well, the connected components. It's important to be, in our case, it's extremely important that it's connected components. So for example, again, in the case of a square, the F2 is, you have 4 components. So four codimension 2 faces. But in fact, as you, well, maybe there are some students, when you define simplicial homology and all these kinds of homologies, it's very important to keep track of the orientations. How you are going to define the boundary faces and all this. And in fact, it was also not trivial, but at the end we got to this definition, which again, it was not completely new, and it's based in examples of simplicial homology, in which we take a face, but we label the face with some orientation on the conormal bundle. So essentially this is just generated by faces, but with a label on the given by the orientation. And this is important because it allows to define the, well, I will tell you how to define the complex. So the complex is essentially, well, it will look like that. I will tell you how the differentials are defined explicitly. So just to tell you that it looks like this. So it's just for example, in the case of a square would be, in the case of a square, essentially what I will try to define is how to define the differentials will be 4 faces of codimension 2. Of codimension 1, there are 4, and then what is the next? So just codimension 0. So no, sorry, just that's the end, right? Codimension 2, codimension 1, and codimension 0. Yeah, and I have to give you the map. But again, I need this label to define properly the map, the differentials. So the differentials are defined as follows. So essentially, the idea, at least to tell you the idea, is to alternate, to give an alternate sum, right? But how to pick up the signs? This is the problem always in these computations. Well, the point is that if you take a manifold of codimension P, for example, let's take a cube. A cube. I don't know if my drawing is nice, but so if you take a face of codimension 3, it is defined by the intersection of 3 codimension 2 faces. And in fact, so the differential is essentially to take an alternate sum, well, alternate meaning the sign that will appear somewhere here, of the faces that defines your face. So here, if I take a F to be the corner of a cube, then I will take a sum with respect to the three codimension 2 faces that define your codimension 3 object. Now, to do it properly, in fact, since the orientation is given by the defining functions of the hyperphases, then you use just alternate. You use just a contraction of the index, which defines your face with respect to the given defining function. So this is what is written here. I don't know if it's clear. Essentially, just taking an alternated sum, but with the induced orientation given by some contraction of the orientation of the conormal bundle. And I will tell you an example, of course, how to compute in practice, because in practice this is a very computable object. You see, this at least it's very combinatorial. Maybe there's a question.
Yes, actually, can I follow? So as far as I can see, there's the causal complex of your defining sequence. There's the standard construction algebraic geometry.
Sorry,
So
I'm not hearing very well. Sorry, could you repeat it?
Can you hear me now?
Yeah, a little better.
Yeah, okay. So if you have a regular sequence defining your submanifold, so your corner, then there is the natural causal complex in algebraic geometry It computes homology. That's what you defined.
Probably, yeah.
So it's it has a name.
Okay.
Has different name.
I guess it's not completely new, yeah, as I was saying. Just in the way I'm presenting it, we find it like that. But even as I was saying, Bunke uses another name. Then we but since we are using these conormal orientations, we call it like that. But I agree, it's not new. Yeah. But still, what I want to emphasize is that it's a very computable object. It's very combinatoric. You give me, I mean, for example, it depends on how the corners close together, right? So, for example, for a square, essentially, a square is what? Well, the four corners of codimension 2, they form a cycle. So this is the idea. So in fact, for this square, so if x is equal to a square, this the H0 will always be 0 in this homology, unless it's a manifold, a smooth manifold. But otherwise, for example, here, in this example, this is just the integer. So it's generated by the cycle formed by the four corners. So it's just integers. And each one is 0. In fact, these are, well, I just put here integer coefficients, but if you, well, here, for completing what I want to say, that this is, I will call in this talk a periodic conormal homology, just the sum of the either even conormal groups or either odd conormal groups. That's it. And then if you want to have fun with these groups, what I'm saying is that you can compute almost a lot of examples, because also you can remark that the Euler characteristic of this complex, of this homology, is essentially the alternate sum of the number of phases with signs. So number of phases of codimension 2, etc., etc. So it's quite computable in examples. But what I claim is that this is the K-theory of these B-compact operators, at least integrally up to codimension 3, and maybe for some kind of interesting products of those types. And in general, I can give an answer just rationally. But yeah, that's what I want to tell you, though. So the theorem of that we show with Mario, and if I have time, I will tell you the integral version that we did with Anne-Marie, because at least in the integral version is very, I think, easy to explain what the indices are. Because here I will explain you the computation that we have in K-theory. But I want also to explain you the indices that takes values in these groups. So the theorem is as follows. So for a connected manifold with corners, because I just care about connected things for the moment, we define morphisms that induce rational isomorphisms. So this is, again, sounds quite classic in other contexts as well. And in fact, explicitly given as follows, that I will explain later I will try to sketch a little bit the proof. But the idea is that, well, there's a quantum isomorphism. In fact, the point about non-commutative spaces is that, well, of course, this B compact operators is already a non-commutative space. But as I was mentioning before, it can be realized as some Lie groupoid algebra. And by using some embedding, as T.S. Singer, and then as was suggested by Kohn in his book, by using the tangent groupoid approach, one can transform the computation in some computation of some space, which I will describe explicitly. And then the nice space, in fact, is a manifold with corners as well. And then, well, you can take a Schoen character and then an explicit map. I will try to explicit this morphism at least up to codimension 3 to show you that it is very explicit, and so at least up to codimension 3. But in general, it's given like that. So it's a quantum isomorphism that I will explain, then Chern character with rational coefficients, and some morphism that will be explicit here between the singular cohomology with compact support of this space and this homology that I just defined. So I will try to explain the theorem. So in terms of the idea of Kohn,
Sorry, I have a question.
Yes.
So this vertical map, could we go to the previous slide?
Yeah.
This vertical map BF goes from cohomology to this conormal homology, yes?
Yes.
Okay.
Yeah. So there's a duality there. Yeah.
So on the right-hand side, both X and O of X are spaces, yes? But on the left side, the upper guy is algebra and OX is a space, yes? So
that's
the
right.
split between upper and lower indices is just going contravariantly due to the fact that one is an algebra, yes?
Yes. That's,
But on the right-hand side is the other way around, yes? Both are spaces.
It's the other way around, but still, I mean, this is, again, the econormal homology is, well, they define it as an homology, not as a cohomology. But what this says is that in fact is the cohomology of some space. So in particular, I will tell you what this space is, but yeah. So that's where the duality comes from. Yeah.
Okay, thank you.
So yeah, this is a good point to remark. This of course is the topological K-theory of a space is also the K-theory of some algebra, but here I want to emphasize that this is can be just topological K-theory of some space. That I will tell you explicitly what it is, and this will be one of the main theorems I want to tell you about. So the idea comes from, well, Atiyah Singer, in fact, but then the interpretation of Atiyah Singer by Kohn in his book when he uses the tangent groupoid. So the idea is of Kohn is, well, to consider. Remember, in the case I was in the manifold with corners that I'm dealing with this paper, these are manifolds with embedded corners. So there's a smooth manifold somewhere that's in this case what contains this X space. So you consider an embedding. This is what Kohn does, but in this case you have to be more careful. And then, well, I just suppose n even because I will need some but periodicity there. And then I take n to be the number of boundary defining functions of the manifold with corners. This little n. And then I consider the groupoid morphism. So here in the left, I have here is a pair groupoid. So the first two components is just pair groupoid, and Rn is the additive group Rn. And I define a groupoid morphism given just by this formula. So it's essentially Kohn groupoid morphism. So just take the embedding into account. So you take, it's very easy to see that this is a groupoid morphism. In fact, it's more than a groupoid morphism. Well, this is a groupoid morphism, but it's what is called a monomorphism. So it's if you have h of some arrow with 0, if and only if the arrow is a unit. So because this iota is an embedding. So if this is 0, it's because x is equal to y. So you are in the diagonal, which is the units of the pair groupoid. The point is that this action, well, this is a groupoid morphism, so it will induce an action of Rn of the big N into the groupoid algebra. But well, here it will induce by restriction some, and here I will explain you what I mean by gamma b because I didn't put it in the slides. This it will be a subgroupoid of this pair groupoid. I will tell you the definition. So where I think I give this space here. So what is this gamma? Maybe let me put some. This gamma bx is a Lie groupoid. So it's going to be given by, I will tell you what is this, but it's what is called a puff groupoid or a blow-up groupoid. So it's a groupoid over the manifold with corners, but where you take the S connected component. So this is why this little C appears. Sorry, let me tell you first the big groupoid. So groupoids have system algebras, and here I will take you. I will show you a very explicit groupoid. So I will take elements in the pair groupoid of X tilde times Rn. So n is the number of definite hypersurfaces, and I will just take this equation. So rho I X is equal to exponential lambda I rho I Y. So because of the hypothesis we did in this manifold with embedded corners, this is a Lie groupoid. And it's a Lie subgroupoid of this one. So then gamma B is defined as the S connected component, so the component of the identity of a groupoid of this groupoid, and then you restrict the groupoid to the manifold with corners. I won't need this later on in the talk, just tell you that there are groupoids around, and in fact, as any groupoid, you can consider algebras. In this case, maximal or reduced are the same because this kind of groupoids are known to be amenable. And in fact, it's quite known now by many people, Montoubert and Nister, and then Debord and Scandalis, and many people have worked out with these algebras. Essentially, it's known, it's quite classic now that these algebras are exactly the B-compact operators in some calculus. In this case, this is exactly the algebra I am dealing with in this paper. So the K-theory of this is what I want to compute. But the fact that you have groupoids simplify a lot the computations, because when you have filtrations and spectral sequences and all that, all these subquotients and all the restrictions will appear geometrically as groupoids as well. So this is what at least allowed us to give computations in K-theory, as I was going to explain. I'm going to explain. So I don't know why I have to erase every time. Sorry. Maybe because it's okay. Well, I will erase it. But the point is that this groupoid morphism that I defined, which is explicit, see, it's just this formula, restricts by restriction, because it's a subgroupoid, to this B groupoid, which is we call it the B groupoid, and then there's an associated action, because you have a groupoid morphism, so you have an action of this groupoid in Rn, which in fact, at the level of algebras, you might think of Rn acting on the algebra of the groupoid, but at the level of groupoids, you can see as the groupoid gamma acting on Rn. So you have a new groupoid, which is what is called a semi-direct groupoid. And in fact, in this particular case, one can show by hand, in fact, that is free and proper. Free because free means that it's a groupoid which is for which the isotopic groups are trivial, and this comes just from the fact that H is a monomorphism, as I was saying. So H of an arrow is 0 if and only if the arrow is a unit element in the groupoid. And proper, well, it says that the S and T maps, so the source and target maps, define a proper map, and can be done by hand in this example. This is something that we showed Jean-Marie and myself in our first paper. It's not so different, no hard to see. And in fact, once you are in groupoids and have a nice free proper action groupoid like this, then as for the case of nice actions of groups, so if you have free proper with nice properties, then you have a space, which is the orbit space, which inherits good properties. In this case, the orbit space is what is called OX. So, and it's in fact is a space which is nice. In this case, in fact, with Mario, in the paper with Mario, we showed how this is exactly a manifold with corners. It's a nice space. And then it's Morita equivalent to this groupoid. So in the world of groupoids, that then reflects in at the level of algebras, if you have Morita equivalences of groupoids, and this will imply the Morita equivalence of the algebras. The point is that with this groupoid in hand, and this is space, so this space is just a quotient. So it's just a quotient by the relation of being in the same orbit. And just to tell you, well, I won't spend too much time in this, but let me explain you very quickly the idea of the theorem. In fact, this space is simple to compute because this space, in fact, admits also a filtration. Here, I take a filtration of the manifold with corners given by, well, I start the filtration in spaces by the higher codimension components, and then you have a natural filtration. What I claim is that there is a natural associated filtration in the OX, because these groupoids are what is called saturated. So these are given by orbits. So the relation that is used to quotient respects the orbits. So in fact, there's a filtration of OX, but this new space has this property that the subsequent differences, so yq minus yq minus 1, are in fact essentially Euclidean spaces by construction. Well, this has to be shown, of course, but it's not so difficult by how it is constructed. So it's essentially, even if it doesn't look like that, in fact, the idea comes really back to Atiyah-Singer and then to Kohn in his interpretation of the Atiyah-Singer index term using groupoids. But now, well, there's a filtration. So once you have a filtration, you can, well, compute spectral sequences. And in fact, since this property, one can show that the singular cohomology of OX can be, in fact, already computed from the first chain complex like this. So the differentials coming from the filtration. And in fact, what we did with Mario is just, and Jean-Marie, is to give an explicit chain isomorphism between the complex that defines the conormal homology and the complex that will define the singular cohomology of the space OX. But this space OX was obtained as precisely as a Thom isomorphism. I recall you the theorem. OX is in fact the action. Is the, well, sorry, I will put it in the slides. Yeah. So how to compute the K-theory of the algebra? Well, there is a quantum isomorphism that first, if you want, it goes to the algebra of the action groupoid. In my theorem, I didn't put it like that, but in fact, there's a first step which is about the quantum isomorphism in some algebra, which is non-commutative, but in fact, which is Morita equivalent. So there's a induced map by a Morita equivalence to the K-theory of this space. So the topological K-theory of OX. So thanks to this, this is essentially again the idea of Kohn, of using these morphisms of groupoids to get quantum isomorphisms, and then Morita equivalences, because you want to again replace your problem, but by some algebras which are in fact spaces. So in this case, gamma B, sorry, the algebra of B compact operators is certainly not a space, but it's up to this quantum isomorphism is Morita equivalent to some space. So this is the idea of the theorem of Mario, Jean-Marie, and myself, that I just recall in here. So there's a quantum isomorphism. This map on the right is very explicit, and this is just the Chern character, which might be explicit in some cases and in other no. It's just as I will show you, I mean, the problem of computing this integrally seems to be as hard as computing integrally this, because we know that the Schoen character is not an isomorphism integrally in general. Okay, so this is just maybe just my motivational part. Sorry, maybe, but I will tell you the rest of the talk. What I try to claim here is that these conormal homology groups are very explicit and computable. So one can ask if this is the case, how about computing the indices there? Because the indices should be then given in terms of conormal cycles. So these cycles are just expressions in terms of the phases, right? So what I mean is how to compute the coefficients explicitly. And then I will give you a sketch of an answer, at least in codimension, in small codimensions. Okay, in codimension 0 is essentially, of course, a Tia Singer. The codimension 1, there's not too much to say because K0 is 0, but I will sketch something. So I will explain this isomorphism that I explained in the general case using this OX, but in low codimensions. So low codimensions, I will start with just illustrated how these computations are done, and also try to explain that it's not only the computation of K-theory that will follow this phenomena, but the indices, the entire indices can be computed using what I will try to explain. So how to compute these groups. So the first is that when in codimension 0, well, this, here in codimension 0, so I will put I will tell you what my notation is. So as A0 is just the algebra of compact operators in this case, because you have a codimension 0 manifold. So essentially you have to choose the isomorphism depends on generators, and well, you choose a rank 1 projector that generates your K-theory group, the K-theory of the compact operators, and then you send it to essentially to X. X is the cycle that generated, in this case, H0, the conormal homology group is generated just by one cycle. That is just the manifold itself. So this is just, well, another way of computing, let's say, the K-theory of compact operators. But from codimension 1, let me explain you what's going on. From codimension 1, one can use filtrations. So A1 is the algebra of B compact operators, and it contains the algebra of compact operators, which I will call A0. So essentially, there's the restriction of the groupoid to the interior, right? So this is the algebra of some groupoid, gamma B, and in fact, it contains A0, which is the restriction to the interior of the manifold, which is manifold with boundary in this case. And in fact, this is just sorry, it's not really compact operators. It's no, sorry, yeah, it's compact operators. What I'm saying, yeah, the compact operators. Well, I will not specify it's L2 of X of the interior. So you have this is quite classic when you compute these things, of course, when you have filtrations. Just to explain you how to do it. There's you take the short exact sequence of sister algebras, which gives you a sequence in K-theory. Because why is this like this? Because some of these algebras have K-theory 0. For example, the K1 of A0 is 0. This is why the 0 appears here. And yeah, and the other side also is 0. So essentially what we did with Jean-Marie Lescure is in our first paper is to compute geometrically using groupoids this differential, which was done before, again, by Melrose and Nister, but we did it with groupoids because we needed to adapt it then for higher codimensions and to what followed. But then what we showed is essentially that we compute, well, we have an isomorphism because A1 over A0 is just, I will tell you this, the sequence in these cases are very simple because A1 over A0 is in fact a sum of per groupoids times R. So this is just algebras that looks like the boundary if you have one component times R. So essentially, it's like compact operators tensor the algebra of vanishing functions at the infinity of R. Well, as many of components as the boundary. So these are easy to compute. Again, this is the K1 of that is just the integers. If you just have one component, and if not, you have as many components as many integers component factors as components you have. So this is the computation, mainly the idea of how to compute. Well, sorry, I haven't finished yet. So this is just how to use the filtration to compute. And then, well, the isomorphism that we were looking for is this one. So this is quite a standard. It's but once you have this commutative diagram, so the computation of the differential in other terms. In this case, in conormal homology terms. So the codimension 2 case is quite similar. In fact, you have just to change the sequences, but taking into account the filtrations. I won't spend too much time in that because it might be difficult to follow in the slide, I guess. So the idea is to take appropriate short exact sequences of the filtration in codimension 2, and then, well, again, compute at least geometrically the connecting maps, which is always the hard problem to do, to how to explicitly compute the connecting maps, which is in fact a theorem, which is here. The computation in terms of conormal cycles, what I call the conormal cycles. And once you do that, well, you might expect to compute to say, well, I can then get the global computation. Here I have to say that in K0, the K0 of A2 is the same as the K0 of A2 quotient by A0. So this is something that people knew, that the K0 indices in this kind of manifold with corners things do not depend on the interior, just on the restriction to the boundary. So this is what appears here. And then just to show you a slide very quickly, for the K1 of the odd codimension cases for codimension 2, well, it becomes a little more complex. So you have not just to take one sequence, but a diagram of sequences in which you have to apply classic methods of K-theory, and then you apply K-theory to the entire diagram to get the result. So just to tell you that this is well published. This is already published by Jean-Marie and myself, and then in H3, for example, you have explicit computations as well. And this homology has very nice properties. So at least in low codimensions, so QNet formulas and all these kind of things that allows you to compute in many examples. But the problem is, again, well, how to compute, right? So how to compute the indices themselves. Sorry, Pedro, how much time do I have? In fact,
You have 22 minutes.
Okay, so again, well, it's I will give an example of how to compute in codimension 2 in 3. Because otherwise it's quite involved. I want to tell you how to compute the indices, right? So the indices means that this map I'm putting here, this thing, is the analytic index that takes values in the K-theory of the B compact. From now on, I will use this notation because it will be more light, but it will be the K-theory of the algebra. I will use a space notation, but in fact it's groupoid. So it's just for notation purposes, because otherwise it's quite heavy, the notation. But my point is how to compute it. And by mean computing is what are the coefficients of the cycles that you get in the right-hand side. This is what it means computes. For example, for X smooth manifold, the coefficient is in fact the Atiyah-Singer index. And The interesting case, in fact, it starts in codimension 2, at least from K0, because for manifolds with boundary, this map is 0 for K0. In fact, for K1 is in fact just a suspension of a T-Singer, but I will tell you, well, what are the ingredients at least to announce the state, the computation. So first of all, there's maps that most of you might know. So essentially a T-Singer, but a suspended version. So I will need some, well, this is just ingredients to state the computation precisely. So you take a manifold, a smooth manifold, Y here, I call it Y, and you take a P, and depending on the parity of P, so if it's the K0, then you take a P even, and it's odd. And then I will define what we are calling with suspended at T-Singer, which is in fact can be also defined using suspended pseudo-differential calculus, as Melrose, for example, or Lesch and Flaum, and people that have studied the operators, which are, because here RP is an additive group. I forgot to say, but for me RP, this component is the group RP. So in fact, the operators which are beneath this construction are invariant, RP invariant translation operators. But here I will propose you a geometric definition that does not depend on operators, just on groupoids for starters. So this is the definition of the Atiyah-Singer suspended morphism. So you take the tangent groupoid of the pair groupoid of Y, which is a groupoid which allows to deform the tangent space or the cotangent up to Fourier, once you take the algebras, into the pair groupoid. So the tangent groupoid allows to give this map, which is here. And in fact, which is, if P is 0, this is really a Atiyah-Singer index morphism. And if not, in fact, it's just up to a Bott isomorphism is in fact a suspended version of a Atiyah-Singer. Here I used to take a Bott isomorphism here at the right, so to get to Z. And not any Bott element, but one element. I did a choice from the beginning. So one generator of the K theory of R, of the K1 of R. And with that choice, all of the computations work. So this is what is called the suspended, well, we call here the suspended Atiyah-Singer index morphisms. And there's another ingredient, which is, so this is just for recall what I just mentioned, this is some indices that will appear in the coefficients of the formulas. And there's another ingredient which is essential in the manifold with corner case, because not all the indices will be of Atiyah-Singer type, meaning that Atiyah-Singer is just for smooth manifolds, and you have just you have the topological computation of that, of course, which is one of the main theorems of the last century, certainly, and my favorite one, that's for sure. But you have also other terms. For example, Atiyah-Patodi-Singer index theorem for manifold with boundary, and it has also been developed in a lot of situations. And here I will define something that we call APS index morphism, because it's related to problems of APS. But these morphisms are not defined from tangent spaces, from classic tangent spaces, but from non-commutative tangent spaces which appear here. I will say a word on this. So essentially, what some people understood at some point, for starters, Claire Debord and Jean-Marie Lescure and Nistor as well, is that in this singular case, the indices of these Fredholm operators can be as well computed from some K theory of some tangent space, but these tangent spaces are not anymore vector bundles, but in fact are Lie groupoids, which are called non-commutative tangent spaces, because they give the right classification of fully elliptic operators of Fredholmness. So the definition of this requires some groupoids which are constructed from the tangent groupoid of Kohn, but are not really the tangent groupoid of Kohn. In fact, the groupoids that are obtained from the tangent groupoid of Kohn by putting out the singular part at 1. So this is why when you evaluate it at 1, these groupoids, you get just the interior part. In fact, this maps, when p is equal to 0, is exactly the Fredholm index of the Fredholm operators in this manifold with corner case, whenever you have Fredholmness. Because as I was saying in the beginning, not every operator in the calculus is Fredholm. You need that the symbol is invertible in some the non-commutative symbol is invertible, sorry. And in that case, you have an index as well, which is given in these terms. And then I can state the formula, tell you at least what is in these terms the formula that we got with Jean-Marie. So again, this is the ingredient. So what we call suspended APS index morphisms, and this will be the ingredients that will appear in the formula. So in the formula for codimension 2, because I will start with this example, you take a symbol here, sigma, and then you look at the restriction of your symbol at every codimension 2 phase, which gives you a suspended symbol like this. And these suspended symbols have suspended Atiyah-Singer indices, and this is what appears in this formula. But you take the sum, because again the actual formula, sorry, what we are looking is the cycle, right? This is the normal cycle, and we were looking to the coefficients. This is what was the goal of this work. And what I'm saying here is that first, well, this sum of all these indices is a cycle, but we are not summing over all the phases of codimension 2, only on those that belong to some cycle. Because other example that I didn't mention is that if your manifold with corners does not close in some way, for example, here I'm not talking, usually I'm talking about compact manifolds, but let me put an example that is not compact. Let me take a square, but remove one of the corners. So a square without one of the corners. This is an open manifold with corners, but it will help me to illustrate my point, is that in this open manifold with corners, there's no, the cycles, the corners of codimension 2 do not form a cycle anymore. So they don't close in a cycle. So this is just to say that this index in the formula is for those corners that belong to some cycle. So this is just this is already in the computation of the conormal homology, because if you don't have cycles, then the group is 0. You might have indices, but the group is 0. So this is the theorem. So in codimension 2, so the computation is this one. So this is a cycle, and the index is explicitly computed like this. And then I will just state the codimension 3 case, and I think I will stop there. But just let me tell you in codimension 2 that this theorem that we have here, it is another version. In fact, it's just another manifestation of cobordism invariance in this codimension 2 case. But from codimension 3 is slightly more involved, because from codimension 3, well, first I need to explain you a small detail of codimension 3, is that up to, so from codimension 3, sorry, no, this is not, this is just odd codimension, sorry, I will skip this codimension 2 odd case, and I will take the codimension 3 case. So this is where I will end the talk. So in codimension 3, in case 0, you have a symbol here. Here's the case 0 of the tangent space, of the tangent groupoid, sorry, which is K-theoretical. It has the same K-theory as the K-theory of the cotangent bundle. So by abuse of notation, I'm just taking the same notation sigma. So sigma is here up to this isomorphism. And then, in fact, we need to choose non-commutative symbols to describe the formula. So in fact, the formula will depend on some liftings, because here I can lift to some non-commutative symbol. Here is the tangent space, the tangent groupoid, sorry, in which I removed the x0 is just in this case is the codimension 3 phases. So I just removed the codimension 3 phases at 1. So it's some kind of invertibility, but up to the codimension 3 in this case. And these non-commutative symbols, because this by some easy computation, this is surjective, in fact, because it comes from some exact sequences. So there are liftings, and the formula will depend. The expression of the formula will depend on this lifting. So I choose a lifting of sigma, and then I restrict it to one given corner. And then I can then tell you what is the expression of the formula in codimension 3. So in codimension 3, for the even case, so k0, so you take a, sorry, let me just erase this thing. So the first thing is that these APS index types, with these choices I gave you above, they form a two conormal cycle. So this is some kind of a boundary, cobordism invariance of these indices, but they, well, more general, because they form a cycle. So they have somehow to, the signs have to agree because of how is defined the delta 2. And then the index is computed exactly as the class, because then in this case is the conormal homology is more general. Sorry, it's not free necessarily. Oh, sorry. It's just the kernel of delta 2 up to the image of delta 3. So this is what it means, this class. Sorry, why this? I don't see why this is like that. But sorry, this is the moment of solitude when we are speaking at some screen, right? Yeah.
They just highlighted it, and I don't know how to unhighlight it.
Okay, me neither. So, well, the point is that these are the formulas, some APS indices that form cycles, which is again something that we want to explore in relation with cobordism invariance. And then, okay, just let me tell you the formula. The odd formula in codimension 3 is even more complicated, because there are two factors. In fact, for codimension 3, there are two factors. There's this factor, and this is the kernel of delta 3 factor. And there are Atiyah-Singer indices and Atiyah-Patodi-Singer indices. And from codimension 3, the thing really explodes, because we have a formula like this, but we're with rational coefficients. And this is, well, something that I cannot explain in here. I would need more time and perhaps more computations. Just let me tell you what kind of things you can say with this, for just by small computations. For example, in the case of manifold with corner of even codimension, just the same computation of codimension 2 works for compute the first factor. So if this is not zero, sorry, if this is not the operator is Fredholm, it has the Fredholm property, then the index should vanish. So for example, you can show that this is just one example, but there are many examples like this, that you have a manifold with corners with codimension 2n and an elliptic operator which has this Fredholm perturbation property. Here I put an H, but it should be an S, this one. Then for every codimension, for every corner of codimension 2n, there's a topological obstruction to this property. So this topological index should vanish. Now, to announce the other codimensions would be more complicated because you need more like APS kind of formulas, not just a T-Singer. And I think, well, I was planning to tell you something else, but I think maybe that will be for another time, unless you have questions. And thank you very much for your attention.
So thank you very much for driving us into a corner.
Thank you.
Well, thank you. I would prefer to have a Blackboard, but well.
I know. Okay, so we have plenty of time for questions. Let's begin. Richard, you are unmuted. It means you want to.
No, I'm okay. I'm not muted, but I'm okay.
Adam.
Yes, so maybe a very basic question. This KB of X, these B compact operators, this is something which is larger than this than the algebra of ordinary compact operator.
Yeah.
And the algebra of ordinary compact operators forms a maximal ideal in B of H. This does mean does it mean that this KB of X is no longer an ideal in B of H? Yes.
Yes.
Am I right?
Yeah, you're right.
Okay.
It's an algebra.
Mm-hmm.
It's an algebra, yes.
And does it depend somehow functorially from this X?
Yes. Well, no, not really. So, not really. I'm not sure of that because the groupoid depends functorially. The groupoid, yes, but the algebra, then this question. I think even for groupoids, I don't really know how to answer. So you have for groupoids, if you have a manifold morphism between manifolds with corners, then you have a groupoid morphism. That's for sure. But I don't know. Maybe you need some support things, and I really don't know the answer to that. Even for general in groupoids, there's no good functoriality, I guess.
Okay, thank you.
Yeah.
Tomek?
Yes, I would have three questions. So the first question is about a second side of this opposite side of this index theorem. So if I understand well, everything is an analog of an analytic index. Even if you are using this conormal homology, this conormal homology is of combinatorial type.
Yeah.
And so this is not this topological part. Do you have something like a candidate for the topological index in this context, or some kind of index problem in the sense of Baum and others?
Yeah, in fact, we do. This is what I was planning to talk at the end, because there is in fact, the computation in the general case is given by a topological index precisely. Because as I was explaining, we compute the K-theory of the algebra by some quantum isomorphism using again the embedding. But the embedding, as I was saying, it was based on the idea of con of a T-Singer, which was used not only to compute the K-theory, but the index. So to give the topological interpretation of the index. And in fact, this is what can be done in this case with appropriate spaces. In fact, the tangent groupoid is in fact a computation. It can be computed by some deformation to the normal cone space. And the computation I was mentioning that we did with Mario can be adapted to the tangent groupoid to have a topological index. But okay, well, and then there are partial answers. No, of course, not a complete answer. But so yeah, there is a topological index of a global topological index. This is one thing, and the other thing is that in every coefficient has also a topological expression, because every coefficient has in its own a topological index computation. So for example, here in this computation, this is a T-Singer, so you can compute it topologically using just a T-Singer. But when you have a T-Singer morphisms, it's more complicated. But still, there are some topological ways to do it, but not topological formula. That's different. But yeah, there are some relations with essentially based on the ideas of Con and Con, sorry, on the use of changing algebras by spaces. Yes.
So if you say something about pathology, is there an eta invariant in this context with corners?
Well, there's not by ourselves. But the problem is that here we are dealing with decay theory. So there is a formula, at least for the K theory morphism of the APS morphism, but the eta invariant is more unstable. You cannot obtain it from the K theory, that's for sure. But there should be. I mean, there is a paper by PAULO, at least in which he computes the contributions of the phases of some index of Dirac operator types. And so there are what I can say at least is that in our cases that we haven't in fact published that part, is that there are contributions, of course, from the phases. This is but should be related with some eta invariants, but I don't really know the answer. I mean, but there are contributions, at least that's for sure, because of how the things are computed. So by the filtration. So there are contributions of the phases. That's but it would be very interesting to come with how the eta invariants appear in there, which I don't know yet. I think it's a nice project in any case.
Very nice. And last question, what are the problems in codimension greater than 4?
Well, at least our method does not work.
So your method is based on short exact sequences.
Yes.
So if in the codimension greater than 4, you have some spectral sequence.
In fact, we have the spectral sequence. The point is that, well, I mean, we have this solution rationally in every codimension. This is in every codimension, but this is a rational solution. But at least the method that we were trying with Jean-Marie was about computing the differentials of this spectral sequence. And I think the problem is, in fact, already in K theory, in topological K theory. So how to compute, in fact, the higher differentials, and we couldn't do it entirely. And as far as I know from Mario, that is more in the topology side, even it seems that it's still a very hard problem for topologists as well. So not only about algebras and manifold with corners, that computing the higher differentials, it's still a huge problem. So this is, for us at least, our method stopped there in codimension 3. We couldn't follow in codimension 4 because we couldn't compute the third differential without the econormal homology rationally. I don't know if this answers a little bit the question, but the problem was about computing differentials, in fact, in the spectral sequence.
But even if you don't know differentials, then you can obtain some 5-element exact sequence. Does it help or not at all?
I really didn't understand it. So even if you don't have differentials, what
but you can derive from the very existence of the spectral sequence some a little bit longer exact sequences where pieces are defined by some kernels or co-kernels, and
well, I don't know if
or not at all.
I don't know. In fact, I don't know if it helps. I think not to give a computation.
No.
Because at the end, I think it's the same problem to compute these Chern characters. You know, it's I'm not sure that it can help.
Okay. Thank you very much.
You're welcome.
Anybody else? I don't see any raised hands. So in this case, Paulo, could you please slide back to the penultimate slide that you showed?
Sorry, which one?
Penultimate.
Last one. No, last one. End of your page. End of your presentation.
This one.
Next one.
Yeah. But no, but the ones you talked about, because I had a question to a slide at which you ended your talk, but then you passed through like 10 slides to go to a thank you slide.
Sorry. Yeah. Maybe it was this
And
one.
penultimate is not the last one, it's the one before the last one. I wanted to ask something and
But I don't know if this was.
No. Next one. Try next one, please.
Sorry. Maybe this one? No.
Oh,
Sorry, I don't remember which one was the ultimate.
no.
Maybe I mentioned this about the codimension 2n.
Yes. Codimension 2n.
And then topological abstraction. Well.
Yeah. Oh yes, I've got it. Yes. So I understand with HFP. So FP stands for Fredholm property, but I was puzzled by H.
In fact, there's another version of homotopical Fredholm property, which I didn't mention in this talk, but it's about having the Fredholm property up to homotopy.
Homotopy. Okay.
In fact, it's very related because essentially in K-theory could be up to homotopy.
Okay.
Sorry, what does it mean? Fredholm property up to homotopy. What do you mean by that?
Okay, I have to remember it, but I think it has the. Well, at the end, it means that they have the same principal symbol. Well, I mean, there is an operator with the same principal symbol. I can say it in terms of K-theory, such that it has the property. This is this is one way to define it. So there's another operator with the same symbol, principal symbol class in K-theory,
which is Fredholm,
which has the Fredholm property. So that means that it can be perturbed to be Fredholm. Yeah. So I guess it can be written down in terms of homotopies of operators, but that's one possible definition.
that's K-theoretic, right?
Yeah.
Again,
it's K-theoretic.
Just saying that the list the boundary vanishes, right?
Yes, that's right.
Okay.
Okay. Since there are no other questions, let us thank PAULO again. Yeah, thank you very much.
Thank you very much, you guys, for
Thank you.
Yeah, and I'll stop recording, but please don't go away.